This meeting is now being recorded.
Okay, good afternoon, ladies and gentlemen. This is David and Candice hosting the webinar. So today's webinar is, the title is Computer Vision, Building an Image-Based Search Engine for Image Classification. The presenter is Andrew Hill. Andrew is a 2017 California Sea Grant Fellow partnered with the Surface Water Ambient Monitoring Program of State Water Board. He recently graduated from the Applied Marine Science Graduate Program of California State University at Monterey Bay. He first became interested in computer vision while manually classifying regions of many aerial images. During his year with the Water Board, he is interested in building the basic tools for OEMA to conduct computer vision analysis and sharing this knowledge with researchers at the Water Board. He is one of our co-workers working beside us. So with this brief introduction, I will pass the presentation to Andrew.
Thank you, David. First off, links at the bottom of our first slide are really hard to see. Sorry about that.
Can you hear him good? Oh. To the mic.
Oh, I see. Yeah, please let me know if anyone can't hear me.
But they are muted.
Okay, so I'm here to talk with you today about building an image-based search engine for image classification. One of the first questions that you have to ask yourself is, why would you ever want an image-based search engine, and what exactly is it? We all use search engines, text-based search engines all the time. We put in text, we get back image, video, text, but what we'd like to do is give our computer an image and have it return to us some kind of text. This has many different applications. Certainly, self-driving cars is one application. And there's many benefits to doing this. Let's say that you had 20 or 30,000 images and you wanted to classify each one of them or count how many objects were in each image. This is an incredible tax on a person's resources in terms of their time. Also, it would be difficult to replicate it. Different people would make different mistakes, and this certainly isn't a very reproducible method. So building an image-based search engine, we identified that we could apply this in a question we've been asking around trash. So in 2015, the State Water Resource Control Board passed the the trash amendments, which addresses trash as a pollutant. So right now, trash that you find on our streets enter our storm drain system. As it travels through the storm drain system, it becomes increasingly more difficult to remove from the environment. So the idea is that if you can get it on the streets before it ever gets into the storm drain system, you'll prevent things like this from happening, where you have trash in a water body that's nearly impossible to remove it. And that's really what the trash amendments are designed to do. They're designed to stop the trash from entering the storm drain system. With devices like these, full trash capture devices are, these are actually partial trash capture devices, but full trash capture devices are required if you're a municipality that has a high density population area. You've got to install these. But there are some municipalities that won't be able to install these devices for a number of reasons. Cost, they are expensive. They're expensive to install. They're expensive to maintain. There are safety issues, and there are jurisdictional issues around installing these devices throughout your region. So the trash amendment has an option, a second track, in which you don't have to install these devices, but you do have to take some measures to control trash entering the storm drain system. And you have to establish a monitoring program to be able to show that you're having an equivalent impact on the amount of trash entering storm drain systems. So to establish that baseline, the current methodology that we're looking at is you would send two people out to an area, and they would walk along a street. And at the end of their stroll, they would turn to each other and estimate how much trash they'd seen. And this is a qualitative estimate. Depending on your training, how you feel, these values might vary dramatically from day to day, week to week, person to person, certainly. So if we could build an image-based search engine where we asked the computer what it saw in the image, this would eliminate a lot of that subjectivity, and we could get quantitative results instead of qualitative results. We approached the city of West Sacramento, and they agreed to mount our GoPro camera to one of their street sweepers. In the lower right image, can you see I hope you can see my mouse, but this is our GoPro camera, and it's pointed directly at the ground, collecting images like the image you see on the left bottom and left top, as well as the top right. So far, we've sent the camera out twice for 2 survey days. We have 2 more days coming up in September to survey the same neighborhoods that we surveyed in August. We've collected about 14,000 images, which total about 30 gigabytes of data. Now, if you want to train a computer to see something, you have to create a lot of different versions of it. So we use these images, these larger images, to crop out different types of trash, and thereby created a trash library with 17 different classifications. So you've got bags, broken glass, cans, caps, lids, cardboards, cigarette butts, cigarette packs, crumpled paper, dental picks. Apparently, you can attach a giant plastic handle to a little bit of dental floss. Didn't know that. And so we made this library of these images. So here are the cigarette packs that we've collected from the 2 days of survey. Here are the cups. Here are the plastic lids. Here are the cigarette butts. This is just from 2 days of survey. And the more images that we collect, the better our search library will be able to train our search engine. So we're looking forward to getting a lot more images in the next couple days, in the next week, actually. So the first step in making an image-based search engine is you have to feed these images to a computer. And this has been a particular challenge for a number of years. But in 2012, there was a pretty big breakthrough that has really given a lot of momentum to the field of computer vision. But first, let's talk about images. So if we think of an image that's 224 pixels squared, and it has an RG and a B channel, there's a lot of different values in there. What we would do historically is we would flatten that image into a single row of values, and this row ends up being about 150,000 values long. There's a number of problems with this. First, that's a lot of information for a computer to look at and take in and deal with. But more importantly, when you flatten an image like that, you're stripping any of the spatial information associated with that image, you're stripping it away. So if you're working at classifying textures, that's not a problem because there's not a lot of spatial information associated with these textures. But if you want to look at a cat or a bottle, there's a lot of spatial information in that image. And until 2012, we really didn't know how to pass that information along to a computer. The advance was convoluting these images. So on the lower left, what you're looking at is a neural network. And on the lower right, what you're looking at is a more recent convolutional neural network. The neural network on the left does not maintain spatial information with the image, and the one on the right does. You'll also notice that the one on the right, down on the far end, there's these flat rectangles, and those actually are representations of these simple neural networks. And then over here, this whole half right here, this is where all the convolution happens. Now, what do I mean when I say convolution? We're talking about matrix manipulations and matrix math. And I'll speak a little bit more about this. The important thing, well, actually, So this is how we feed images into a computer. But how do we make it learn what an image is? So if we look at this neural network on the left, we've got 7 inputs right here. Let's rethink of this as a 7-pixel image. And on the right, we've got a three classifications. And in between the two, we've got this matrix of weights. And this weight area is where the real magic happens with how we train these computers to recognize things. But, so we put our image in these 7 pixels. We multiply the 7 pixels by the weight matrix, and we get different values for these classifications, 0 to 1, 1 being this is absolutely the classification, 0 being this is absolutely not the classification. So initially, we feed an image in, the weight values in the middle are random, and so the classifications are random. And it doesn't do us very good. What we do to train the computer is we actually hotwire the classifications by saying this is a 1, and the others are zeros, depending upon what your classification is. And we use backpropagation to alter the weight values a little bit, just a little bit. And we do this again and again and again, 10,000 times for each classification. And that's how we adjust that center layer of weight values so that when we put in an image with 7 pixels of a cat, the cat category is going to be a 1 value, and everything else will be a 0. That's the basic concept of how we use backpropagation to train these things. Now, if we look at this larger model, the convolutional neural network, in between each one of these squares, there's a weight layer. So there's a lot of weight layers. And this particular model that you're looking at is called the VGG16. It's a well-performing model. It doesn't really matter what it is, except that if you train this model and you have all these weights on hand, the file, it's just one file, ends up being about 90 megabytes. And with this file, I can send you this file, and you can load it on your machine, and you can give it a picture of something, and it will classify that picture in the exact same way that my computer will classify that picture. So that's reproducible, and it happens pretty quickly, on the order of 10 to 20 seconds. So to visit this idea about the weight layers, because it's a little bit much to digest right away, all I really want to look at is the lower left-hand corner where there's Alberts over there. And those 4 blue to red squares represent weight layers. So we multiply Albert by each of those weight layers. And we get a new Albert. We actually get 4 new Alberts. And then each one of those 4 new Alberts gets multiplied by a whole other series of weight layers. And we get a lot more Albert Einsteins. And ultimately, as we get further and further from the original, when we get down here, we start to see the visual representations of these things don't look anything like Albert Einstein. But it allows a computer to distinguish between Albert Einstein and Thomas Jefferson. And that's really all we need to know about this slide. So convolutional matrix math is complicated, and I've read quite a few of the papers, but let me be clear, I don't understand it entirely. It's complex. There's plenty of resources out there. This is the loss function that we use to train our weight layers, to minimize error amongst the weight layers. There's plenty of resources out there. If you want to learn more about convolutional math, you can. But that's not really why I'm here talking about this today. So we had this idea that building a image-based search engine could be useful to monitoring trash. That's the idea. And we got the images about a month ago. And we've made some progress, but we still have a lot more to do. So right now what we have is a functioning network, a functioning neural network that can detect whether or not an image is of survey-grade quality. So this sweeping truck was driving around collecting images every 2 seconds, and a lot of the time they weren't sweeping, or they were just driving to get to a neighborhood, or they were turning around. And computationally, we don't want to send all of those images to this computer. We want to kind of weed out all the images that aren't part of our survey. The good news is we got about 90% accuracy. That's great. So the image on the left is just an empty street. The image on the right includes a curve, the staging area for the storm drain system. And that's really what we want to be looking at. The second part of this, sorry, I didn't include an image here, but using all those clipped images of cigarette butts and cigarette packs, all those 17 categories of trash, we ran this through our convolutional neural network, and we were really surprised we got a little bit greater than 90% accuracy right out of the box. And this is surprising because, you know, trash in, you expect trash out, but we got really great results. Sorry about that. We'll improve this result as we refine the images in the library. We got to get rid of bad images, low resolution images. This number will improve, especially when we get more images after the surveys in the next few days. So, what this means, now we have a trained network, is that we will be able to identify trash in pictures in quantitative ways. We'll be able to say how many pixels are in a trash class and how many counts of trash are in that image. So this is the goal, right? We want to look at an image and be able to say how many straws there are or how many pixels of cardboard there are. We're still trying to figure out exactly what metrics are going to be most useful to municipalities, water body managers, street sweepers. But the idea is that we'll eventually have a CSV file that has lat longs, timestamps, and these quantitative metrics for the trash in these images. So we haven't figured out exactly how to use our model and get these values yet, but that's what's next. So on the left, there's a process called conditional random fields with recurrent convolutional neural networks is the full title. It's a little bit much, but they've published a paper and they've provided their model, and their model includes identifying horses and dogs and cars and airplanes and bicycles and bottles. So I thought, why don't we just use their model and see if it can identify some of the bottles in our trash pictures. It hasn't been trained to see trash at all. It's been trained to see birds and dogs and bicycles. But it did recognize these images of these bottles, and it counted how many pixels are just bottles, and that's really promising. This is kind of a first test run, and when we point our own developed weight matrix at this, I expect that it will do much better than this. So that's exciting. The other aspect that we're exploring is regional proposals for these convolutional neural networks, where instead of getting a pixel count, we get object counts for different types of trash. So in the picture on the right, you see that there's two people, one horse, one dog, and a car. We're hoping to be able to do that with trash. The goals of this trash vision project study, and ultimately of developing an image-based search engine, we'd like to make all this data and the methods open source and available. They will be available on data.ca.gov. They're also available, or will be available on my GitHub account. And we'd like to investigate whether or not this approach could be employed statewide. Just because you're a municipality that has to monitor because you can't deploy full trash capture devices everywhere, doesn't mean that you wouldn't want to use this in your city to be able to understand how trash is moving through your system and what types of trash are really the big players. There's very little cost to deploying this. People are already sweeping the streets. All they'd have to do is mount a camera. There's very little upfront cost to being able to do this monitoring. And that's one of the real advantages of computer vision and image-based search engines. So we'd also like to pass this analysis on to data managers and water body managers and see what kind of input they have and feedback they have. But also we think that this could impact how people go about sweeping their own streets. So we have a lot of hope for employing this, and we hope that it can do a good job and ultimately see this happen statewide. So with that, thank you for letting me drone on about an image-based search engine. Thank you very much. Any questions?
Yeah. You guys have questions?
All guests have been unmuted.
Yeah, people on the phone can ask if you have questions now. Any questions?
Hi, I've got a question, Andrew. This is Steve Steinberg at SWRCB down in Southern California.
Sure.
Well, we've worked with similar kinds of things in other contexts and addressing some of the things you talked about at the end, like identifying objects versus pixels and so on. But one of the most complicated issues, and I'm curious what your take on this is, in kind of this close-range photogrammetry, which is really what you're kind of doing, or close-range image processing. Do you have any sense of how the background influences your accuracy rates? And in particular, I'm thinking about things like concrete versus asphalt, wet concrete versus dry concrete, sort of those things that might complicate sort of the overall consistency of the images over time. So if I go back on, after a rain and want to see did I get more or less trash on the same street sweeping, trip on a dry day, or another example might be partially occluded imagery where the bottle is under a bush and I only see half of it. Things like that. Do you have any sense of either how well your algorithm might be working in that sense, or how you might address those things going forward?
Sure. Yeah. The background certainly is an issue. I do know that some methods, the conditional random fields, employ a step to include a lot of different background types, and so it would actually classify the background as something, and it would just not show you those results. But I believe that these methods are fairly robust to background. Different background types and different background conditions. The region proposal methods, I believe they do not include any type of background classification. They use feature maps of the intermediate convolutional layers, and those feature maps pretty much highlight regions of objects. And through that process, you can get around having to identify any kind of static or continuous background. At least that's my understanding thus far.
I will give chance for people in the room. Go ahead and ask.
Can you calculate the total weight of the trash, or can you calculate the weight by the itemized weight, by the bottles, by the cigarette box?
Yeah, that's certainly something that we would like to do. We would like to convert number of pixels of crumpled paper to a weight value. But this is a pilot study, and conversions like that would require a lot of research around the relationship between what we see in an image and what we actually measure after we pick it up. At this time, I don't think we're going to try to make any conversions. We're simply going to stick with pixels per trash class. So at this time, if we can prove that this concept works, that we can show distribution, we can make some heat maps of where these trash classes exist, I think that'll be plenty of information for a larger study and a more refined process to go underway.
And is there any question? No? Go ahead.
Do you have to know this technology has been used to sort trash for recycling? Recycle bin enclosed and stored in?
I'm sorry, say that again?
You have to know if this has been used to sort materials for recycling. improve the accuracy of recycle stream flow coordination and increase yield?
I don't know of any particular instances, but it certainly seems like this would be a great application of it. This technology. We really saw an explosion in this technology in the past 3 or 4 years. Google's self-driving cars employ a lot of these same principles and mechanisms to do what they do. They recognize objects. That's pretty much how they operate. So if you have a machine that's sorting recyclables, absolutely, they could certainly build something to improve their current system. One of the exciting things about this technology is that it's so new and it's so powerful. And many of the questions that we kind of stopped ourselves from asking in our various fields of research are kind of opening up to us. We can ask questions about this big data using images. So it's a very exciting time to be working with this stuff. Yeah.
Earlier in the discussion, you mentioned spatial information as part of the image. Were you referring to the geotag type metadata that accompanies the input image and maintaining those spatial pieces of information through the convolution process?
So the question was spatial information as in like lat long metadata associated with the image. Yes. No, I was actually so when you look. No, not that information does not go into this system. It can be held and incorporated, certainly. I was talking about if you're looking at a picture of sand, nothing but sand, there's very little spatial information in that image. Now, if you put a card on that sand and take a image or take a photo of the card in the sand, the card has spatial information. There's corners, there's a center, there's a top, a bottom, there's sides. That kind of spatial information can be lost if you just flatten this image before you perform these convolutions.
So you are getting back to the location of the trash probably after the fact. Well, after classification, you go back to the original image and see where it was taken long last.
The output that we would like to generate would be a CSV file with lat longs, timestamps, the image name, and then the classifications of trash with their pixel counts and or their numerical counts.
So this is Lawrence, Region 2 Water Board. So do you build the library, like meaning by that, of objects? So this is a bottle. So do you do the machine learning part, or is the library already available and then used by the computer to recognize what the objects are to the image analysis system?
I believe I heard you right. So we have a folder full of these cropped images, and that's our library. And we're going to add to that library and refine it, make sure we didn't make any mistakes, throw out the bad images. But once we've built a stable library, we'll train a network with that library. And then to give this capability to anyone else, we don't actually have to give the library. We can. It's going to be available if people want it. But you can just get the trained model and use a trained model. So you don't actually have to do any training. You can just pick up the model and use it right away.
Okay. And so then let's say that I want to add an object to that library as I'm conducting an inspection, meaning by that maybe a bottle type is not recognized by the system as a bottle. Can I do that dynamically, or do I need to use another kind of device in order for it to build that library and add what that bottle is?
I don't know about adding that dynamically. What I would do, I'm sure that will come around in the years to come. But right now, the method that I know about is adding a new category to your library, and then retraining the whole network.
Okay, thanks.
Jonathan Gay from the server operations for Onboard. I was kind of curious about how fast the pace of growth would be for the imagery files, capacity of that. Do you have an estimate of, you mentioned like 30 gigs or so of data that you did for so many pictures, so wanted to find out, are you guys internally thinking about storing, or are you going to go cloud-based on storage for the portal?
Those are questions that are beyond my understanding of the capabilities of these various municipalities. Right now, we're keeping all the data, but it may be that we only need, a GoPro, every image that it takes is, I think, 3 or 4 megabytes. We may not need to keep images that large. We might be able to downsize those images to a fourth of that size. That'll come down the road. But as far as maintaining the images, it may not be necessary. In terms of open data and transparency, it would be great if you were a municipality and you kept these images on hand so that you could, you made a new, better model, you could rerun these models on these old images and get an updated understanding of how this trash has changed in your system through time. But there may not be a reason to hold on to these images long term.
Like retention, determination of retention has to be defined as well.
Certainly, yeah. This is by no means a final product. This is still in the initial stages of development. In many ways, it's just a proof of concept. Nonetheless, it's...
What language is doing the processing for the convolution aspect?
There are a number of different... I work primarily in Python. There are a number of different languages. There's frameworks to do this type of learning. The big ones are Caffe, Keras, Microsoft has one, Google has one as well. This was all done in Caffe and Keras.
So we'll take 1 or 2 questions quickly and finish the webinar. Is there any question from the phone or from the room? Okay, Andrew, thank you very much for this excellent presentation.
Thank you for your time.
We'll see everybody next month. Thank you all for participating. Bye.
Thank you.
Thank you.
The host has left the meeting. So at this time, the meeting will come to an end. Thank you and goodbye.